Let me start this lecture by looking at the order of a permutation. So the idea is that we want to know an order of a permutation given that we have the cycle decomposition. So let's say we have alpha, an element of Sn, of the permutation of n elements, and you know that alpha is a product, or to say it much better, a composition of permutations. So cycle C1, C2 up to Cm are all of them cycles, and more importantly, they are disjoint. As we saw in the previous video, you can always take a permutation and write it as a composition of disjoint cycles. So we have that type of permutation, and if we know that, then and also we know that the length of every one of these cycles is L sub I. So this, for example, has a length L1, C2 has this length L2, and this one has length Lm. So if we know all of that, then the order of a permutation, and this is what the notation here means, is the least common multiple of the lengths of all the disjoint cycles that you have in that decomposition. So what this means, this theorem means, is to be able to find the order of a permutation, you only need to know the disjoint cycle decomposition of that permutation, and the lengths will give you the order, finding this order with this formula right here. Now this is another theorem that I'm not going to prove by the same reasons I mentioned before. Alright, but I want to give you an example of this to see how this works. So let's see an application of that theorem. So let's look at this. Determine the order of this permutation. So the permutation alpha here, as you can see, is the product of these cycles. So this is a 3 cycle and these 2 cycles, and you can see here that they are disjoint. Now that's something that's very important. Before you apply this theorem, you have to make sure that the decomposition of your permutation needs to be in disjoint cycles. If it's not, you need to put it in a way that is disjoint cycles, otherwise the theorem does not apply. But in this case, our permutation is disjoint cycles, so we had, okay, so we're gonna consider this alpha as a permutation of in S7, so it's a permutation of the numbers 1 through 7. So let's look at that. So by the theorem, the only thing you need to do is just look at the length of the cycle. So this is length 3, length 2, and length 2. So because this composition in disjoint cycles, we're going to apply the theorem, and we can say that the order of the permutation is the least common multiple of 3, 2, and 2, which are the lengths of the cycles, and the least common multiple of that, all of that, is 6. Okay, what does that mean? Let's recall what order means. So what order means, remember, is that this alpha to the 6 is the identity. Remember, the identity in permutation is the function that fixes everything. So alpha to the 6 will be a function that fixes everything, and any other power of alpha lower than 6 will not be the identity. So that would be the meaning of order here. So something that we talked about already. Alright, so a little bit more interesting example using this theorem would be this. So let's look at this example here. Determine the order of all the elements in S7. Now, in the previous example, we look at the order of one element. What we want to do here is look at all the older orders of all the elements in S7. Okay, let's look at this. This group of permutation of 7 elements with the binary operation of composition has 7 factorial elements. Now, this is something that we saw already in another video. So the number of elements of Sn is n factorial. So in this case, will be 7 factorial. And if you actually simplify this is going to give you this number here. So this group has this many elements. That's quite a lot of elements. Now, it is unfeasible to check all these elements one by one. So what I mean unfeasible here is, if we do this by hand, imagine having to check every single element of S7 and then find the order of that element. That would be unfeasible in the sense of doing it by hand. Of course, if you write a computer program, the computer program will probably just do it really fast, but the idea is we want to do this in a smarter way, so without having to check every single one of those elements. Now, if you could check each one in 2 seconds, it will take you 3 hours. So if you check this many in 3 seconds, it will take you about 3 hours, but that's not what we're going to do. So we're going to take a much better approach, and the approach is that if you look, let me go back here to the theorem. If you look at the theorem, the only thing that determines the order of a permutation is the length of the cycles, not what is inside that cycle. So in this example we did 2, 5, and 4, this contributes nothing to the order of alpha except for the length. So the only thing that matters here is the length of the cycle. So what we want to do to solve this particular problem is look at what possible number of cycles, or the structure of every permutation is in terms of the cycles. And this is what I mean by that. So we know that the elements of S7 or any Sn can be written as product of cycles and disjoint cycles. We're going to look at all possible cycle decompositions, and then from there we can actually get the order. So I'm going to do this in 2 columns. So here in this column, I'm going to write down the cycle decomposition, and in this column, we look at the order. Now, one cycle decomposition that you can have of an element in S7 is just a 7 cycle. That's the largest cycle that you can have in an element of a 7. So this will be the elements 1 through 7, not in that particular order, but in some order. So that has length 7. Now, by that theorem, the order of this will be the least common multiple of 7, which is of course 7. So the order of this is 7. Now, one important corollary of that theorem is that a cycle, the order of a cycle is its length. So this is length 7, so the order is 7. Okay, what else can happen? Another thing that can happen is you have a 6 cycle and a 1 cycle. Now remember, in our representation, we usually ignore this, but in this particular case, we want to look at this kind of decomposition, so to make sure that we have always a permutation of 7 elements. So we have a 6 cycle and a 1 cycle, because the order of a permutation that looks like this is only the LCM, or the least common multiple between 6 and 1, which is 6. So any permutation that has this decomposition will have order 6. Another way in which you can represent a permutation of 7 elements is by a 5 cycle and a 2 cycle, because it gives you 7. And then the least common multiple of the length will give you the order. So in this case, will give you 10. Another way will be a 5 cycle and 2 1 cycles. And in this case, the order will be the least common multiple of 5, 1, and 1, which is 5. Now, what you want to do is you want to write down the type of permutation depending on the structure of the cycles. So we're going to end up looking at all the possibilities for all the structures. So then we can have a 4 cycle and a 3 cycle. And then the order will be the least common multiple of 4 and 3, which is 12. And then we could have 4 cycle, 2 cycle, and 1 cycle. And again, apply the theorem to get order 4. A 4 cycle and 3 1 cycles here. The LCM will give us the order. In this case, it will be 4 by taking the LCM. You can also have a 3 cycle, and a 1 cycle to have a permutation of 7 elements. So the LCM will be 3 here. A 3 cycle, a 2 cycle, and a 2 cycle. That's going to give us another permutation of a 7 element. The LCM will be 6 in this case. Then we can have a 3 cycle, a 2 cycle, and 2 1 cycles. That's 6. We could have a 3 cycle and 4 1 cycles. That's going to be order 3 by taking the LCM. You could have 2 cycle, and 3 1 cycles. The order will be 2 by taking the LCM of the length. Again, the same thing. 2 cycle and then 5 1 cycles. The order will be 2. And then 1 cycle, 1 cycle, 1 cycle, 1 cycle. The order, of course, will be 1. Now, in this case, the last one is just the identity, because it fixes every element. For this one, this is what we call 2 cycles only, because remember with our notation, we usually ignore this in our notation. Now, all the possibilities that we had here, those are all the possible ways in which you can write down a permutation as a product of cycles. If you actually are looking at this kind of decomposition, if you think about it, this decomposition is actually the number of ways in which you can write down 7 as a sum of numbers. So 7 is 6 plus 1, 5 plus 2, 5 plus 1 plus 1, 4 plus 3, 4 plus 2 plus 1. So it's the number of ways in which you can express 7 as a sum of natural numbers. That's called partitions of a natural number. So the number of partitions determines the type of a structure of a permutation that you can have. So the possible orders of the elements of S7 are, so the identity, 2, all these numbers that you see here are the numbers that we got from this list. So 1, 2, 2, 3, 6, and so on. So the possible orders of all the elements of S7 are 1, 2, 3, 4, 5, 6, 7, 10, and 12. Now, we didn't have to list the 5,040 elements of S7 and calculate the order for each one of them. That was not necessary because of the argument that we just did. We only look at the structure, and that was going to give us the order of the elements in S7. So that's the important part here, that we've solved the problem using a much better way than doing the checking of one by one here, the elements. All right, so that was an important application of that theorem. Now, before I go into the next thing, a 2-cycle AB is also called a transposition. It's called transposition because interchange the elements A and B here, and everything else is fixed. So whenever we talk about this 2-cycle, I'm also going to call it transposition. Now, the next theorem is the following. So this is called a product of 2 cycles. So what the theorem says is the following thing. Every permutation in Sn, when n bigger than 1, is composition or product of 2 cycles or transpositions. Now, we talked about how every permutation is a composition of disjoint cycles. The cycles could be of any length. What this proposition is saying is that every permutation is composition of only 2 cycles. It doesn't say disjoint. It doesn't have to be disjoint here when you have 2 cycles. All right, so in this theorem, I'm going to prove it. And you will see why. So the idea is quite clean. So let's look at this. So every permutation Sn is composition of 2 cycles. Let's start with the identity and look at how we express the identity in Sn as a composition of 2 cycles. Now, the identity is the function that fixes all the elements from 1 through n. We can express the identity as a product of these two cycles, 1, 2, and 1, 2. Now, if you look at this composition that we have here, this fixes all the elements from 3 to n. And it also fixes 1 and 2. If you go by the way we evaluate this function at 1. So if this is evaluated, 1 goes to 2 and 2 goes to 1. So 1 is fixed. So 1 is fixed, 2 goes to 1 and 1 goes to 2. So 2 is also fixed. So this fixes everything. So this here has to be the identity. So we have just proven that the identity is a product of two cycles. Notice here something important. These are, of course, not disjoint. And that is usually what happens is when you express something as a product of two cycles, you usually end up with something that is not disjoint. Okay, so how do we prove this in general? Now, by a theorem, we know that every permutation of Sn is a product of disjoint cycles. Not necessarily two cycles. So let's use that to prove this theorem. So what we mean by this is whenever you take a permutation in Sn, you can always write it down as a product or composition of disjoint cycles, where these C1, C2 up to Ck are all cycles of various lengths. So this, for example, could be length 4, length 5, and so on. Now, how do we prove that alpha is product of two cycles? That's what we want to prove. And this is the main idea here. Now, if we can prove that every cycle is product or composition of two cycles, then we will be done. Why? Because imagine if we do this. This is a cycle, let's say, of length 4. If I can prove that this cycle alone is a product of two cycles, and this cycle is a product of two cycles, and every other cycle here is a product of two cycles, then of course everything here will be product of two cycles. So to finish this proof, we only have to look at one cycle and prove that for a particular cycle, for any cycle, we can express it as a product or composition of two cycles. So let's do that. So let's consider a general M cycle. So let's say the X cycle is A1 through AM, where these are arbitrary elements and M could be bigger than 2. Now, we can express that two cycle like M cycle like this. So if this is A1 through AM, so remember this means A1 goes to A2, A2 goes to A3, and so on, and AM goes to A1. What we are claiming is that this M cycle is the product of these two cycles. So this is A1 AM, A1 AM minus 1, A1 A2. Now, how do you check that these two things are the same? Let's look at this. This here in this cycle, A1 goes to A2. The same thing needs to happen here. So if I evaluate A1 here, A1 will go to A2. A2 is none of these two cycles, so the A1 goes to A2. A2 will go to A3. The same thing is going to happen here. All right. What happens, let's say, for example, with these other things? They also going to get exactly the same treatment for all the other things here. So if you think about this one and this one, I'm not going to check each one of them. Think about why this whole product here will actually be equal to this one. And I will prove the theorem. So this is going to prove the theorem. Now, I know this might be a little bit difficult to understand. Let me give you an example on how this actually is going to work. An example is not a proof, but it gives you an idea on how the general proof is going to work. So I'm going to say that is proof. Let's look at this 5 cycle here. 2, 4, 3, 5, and 6. It's a 5 cycle, let's say, in X6. Now, by this composition that I have here, how do you express that 5 cycle is a product of 2 cycles? This is what you're going to do. You look at your cycle, which is this one right here. This is your cycle. And you're going to start doing this. You're going to pair the first one with the last one. That's going to be the cycle that you put here. And then you pair this one with the next one, 2 with 5, and that's your next 2 cycle. And then the 2 with the 3, that is your next cycle right here. And then finally 2 with the 4, and that is your last cycle that you put there. Now the claim is that this one is exactly the same as that, as I mentioned here in the theorem. Now, how do you check that? Okay, let's do this in this particular case. Okay, so here 2 goes to 4. The same should happen here. Yes, 2 goes to 4 and 4 does not appear here, so 2 goes to 4. Let's see 4. 4, where it goes? 4 should go to 3 here. Let's see here. 4. 4 goes to 2, but then we need to plug this one in here. So 2 goes to 3. So 4 goes to 3, and 3 does not appear here, so 4 will go to 3. So that's going to take care of this part. Let's see the next one. 3 should go to 5. Let's see that. So 3 goes here, is being fixed by this one. Now 3 here will go to 2, and 2 will go to 5, so 3 goes to 5. So 3 goes to 5. 5 goes to 6. Why? Let's see. 5 here is being fixed by this one. It's also being fixed by this one. And then 5 goes to 2, and then 2 goes to 6, so 5 goes to 6. Now 6 will have to go to 2. Why? 6 is here in this part. So it's fixed by this one, fixed by this one, then 6 goes to 2. So these two things actually do the same thing. So this 5 cycle is a product of 2 cycles. Notice that this decomposition here is not disjoint. The number 2 is common in all of them. And that's the remark I'm going to say. The previous theorem does not say product of disjoint cycles, because it usually is not. So when you have a permutation, you can write it down as a product of 2 cycles, not necessarily disjoint, but it is important that is 2 cycles only. Alright, so that's all I have to say for today. So we will continue with more theorems and results about the permutations. And I'm going to tell you where this is going. The idea here is that we're going to look at the decomposition in 2 cycles, and we're going to classify the permutation in terms of that 2-cycle decomposition. So the 2-cycle decomposition is going to classify permutation in 2 big groups, between the even permutations and the odd permutation. But we will talk about that in the next video. Alright, so that's all I have to say for today. Take care and good luck.